Okay, can you hear me? Welcome everyone to the afternoon session, and we start with Adolfo Guarino, who's going to tell us about the ubiquity of S-folds. Please.
Hi. So thank you very much. So I would like to thank first of all Ioannis and the rest of the organizers for the invitation to speak today here, and also apologize for the change of schedule. So my talk was supposed to be yesterday, but then I was also supposed to take an airplane, and I ended up at the hospital, so it was a bit a tricky day. But luckily everything went okay. So today I will tell you about this kind of configurations of type-2B string theory that go under the name of S-folds, and this is based in this paper I wrote together with Colin Sterks, my previous PhD student, and now postdoc in Padova, and also with Mario Trillante from Torino. And also I will mention some work in progress that we are working on. Okay, so let me just start by saying that there is a whole literature on something that is called consistent truncations, specifically like how to truncate 11-dimensional or type 2 10-dimensional supergravities down to 4 dimensions, and these consistent truncations have been crucial in order to develop precision tests and applications of low-dimensional holography. In this particular case of this talk, the duality between ADS4 and 3-dimensional conformal field theories. The prototypical example, and is the one that I will be focused on today, is the case in which you take 11-dimensional supergravity, you place it on a 7-dimensional sphere, and then you end up in a description of fluctuations of this 11-dimensional supergravity on this 7-dimensional background. And essentially you end up with an effective description of these fluctuations, and the description precisely fit the form of n equals 4, d equals 4 supergravity. Okay? So this is the specific example I will discuss today. So how to place this 4-dimensional theory in 11 dimensions was done 25 years ago by Svetic, Liu, and Pope, and I will just mention this and provide an alternative. So let me just start by showing what is the, actually I don't see, so my eyes is not working very well. So let me start just by summarizing what is this 4-dimensional n equals 4 supergravity. So the field content of the theory, the bosonic field content, is the metric. Then there are 6 vector fields spanning the gauge group, which is SO4, so 2 copies of SO3. And then there is a complex scalar, I call it tau, or if you want, 2 real components, chi and this psi over here. So this is the field content. And then the action of the theory is the one just here. So you have the Einstein-Hilbert term, the kinetic terms for the 2 scalars, some scalar potential that is here, and then you have kinetic terms and topological terms for the vector fields. Okay, in particular you have these ones for the first SO3, and these terms over here for the second SO3. So it's like a well-established setup. So what do I mean by having a consistent truncation of 11-dimensional supergravity down to this 4-dimensional supergravity? I mean the following. So the whole story, so the goal is to place these 4-dimensional fields into an ansatz of your 11-dimensional fields such that things are consistent. And by consistent, I mean that if you compute the equations of motion in 11 dimensions, so you have the Bianchi identity for F4, which is this one. Also the equation of motion for F4, which is this one. So this F7 here can be seen as a shorthand notation for this specific combination of F4 and E3. So if you compute Bianchi identities, equations of motion, and Einstein equations of 11-dimensional supergravity, and you plug the ansatz, whatever the ansatz is, for your 4-dimensional fields into 11-dimensional fields, what you get at the end of the day is nothing but the precise equations of motion that follow from this action. So in particular, if I just focus on 2 vector fields, let's say the Cartan-Abelian subalgebra of SO4, just for simplicity, but I can extend all these expressions for the non-Abelian case. But let me just focus on the U1 cross U1 that is inside SO4, just to show simpler equations. So when you plug the ansatz by Svetic, Liu, and Pope into the 11-dimensional fields, they boil down to this set of equations here in 4 dimensions. So the first two equations you get are nothing but the Bianchi identity for the vector fields. The second equations you get here are nothing but the equations of motion for the vector fields, where again F1 tilde and F2 tilde are nothing but, this is like a shorthand notation for this. This is what is called, so essentially this is the usual electromagnetic duality in 4 dimensions, in which the Bianchi identities and the equations of motion can be treated democratically. And essentially these are the magnetic field strengths, which are not independent from the electric ones. In particular, you have these self-duality relations. And then you also get the equations of motion for the complex scalar tau, the one that follow from this action, and also the Einstein equation that follow from this action. So in the end of the day, you start from the 11D equations, you plug an ansatz, and then these equations really reduce to the equations of motion of the 4-dimensional theory, precisely the equations that follow from this action. Okay, this is what people mean by having a consistent truncation. So let me go back to the action. So this is the 4-dimensional action, and what kind of solutions people have explored here. So people, first of all, study solutions in which only the rich scalar and the scalar potential are there. So essentially configurations where the scalars are constant, in particular the complex scalar tau is 0. And in this solution, so is I in this parameterization, sorry, and this is an ADS4 solution that when you place it in 11 dimensions, what you get is the famous ADS4 cross S7 Freund-Rubin solution. Okay? And then we know now, after many years, that this ADS4 vacuum that uplifts in 11 dimensions to ADS4 cross S7 is precisely dual to the 3-dimensional conformal field theory of ABJM. Okay? So ABJM is the field theory dual of this specific ADS4 solution. But then you can search for more complicated solutions. For example, solutions in which the scalar fields develop a profile along certain direction, certain radial direction, let's call it. In this case, you can construct some type of solution that is called a Janus. So a Janus is a 4-dimensional solution which is not ADS4, it's ADS3 times some radial direction. And the ADS3 is a proper ADS3. It's not a warp ADS3 in the sense of the type we heard about this morning. I will come back to this at the end. So this is just an ADS3 solution in 4 dimensions that once you place it in 11D, it goes to an ADS3 cross some radial direction, cross S7. And then these solutions are dual to what is called interfaces in ABJM. So essentially configurations in the field theory in which you have the field theory living in two half spaces and there are certain properties changing from one side to the other. And the change of the properties in the field theory from one half to the other half of the space is related to the running of the scalar fields. And of course, there have been a lot of works on ABJM interfaces or equivalently Janus solutions in the gravity side. And then maybe the most studied type of solutions are solutions of the form ADS2 cross sigma 2, which are examples of black holes which are asymptotically ADS. Okay? So in this case, what you have is a solution in which everybody is activated, vectors, scalars, everyone runs. So they are like complicated solutions, let's say. And essentially what you get is that they are in ADS because there is a cosmological constant. So in the end of the day, you have solutions that interpolate between an ADS4 in the UV and the horizon configuration, which is the ADS2 cross sigma 2. And this holographically describes in field theory the ABJM theory. When you place it on a Riemann surface, then you have to add a topological twist and certain things, and you describe essentially like flows across dimensions in the field theory. And there is a really long, vast literature on this kind of configurations. Okay, so all these things have been done in this 4-dimensional supergravity for which an embedding in 11D is known. Okay. So what I will tell you today is that all these solutions, absolutely all these solutions that have been embedded in 11 dimensions can alternatively, and this is the really important message, I will pass it today, can be uplifted to type 2B as well. And the whole meaning of the story is not known in type 2B. So there are 25 years of research on ABJM and all these solutions, and I will show today that this exact same theory can be embedded in type 2B supergravity. And the configurations in 10 dimensions will be of the form what is called as an S-fold. Okay? So this is the main message. Any solution of n equals 4, d equals 4 supergravity, and also n equals 3 and n equals 2 because they are subcases, can be oxidized to a configuration, which is a non-geometric configuration. I will explain this. That is called an S-fold of type 2B string theory. So everything that has been done in the context of 11-dimensional supergravity and AVGM can be repeated or reinterpreted in this context of type 2B S-folds. So the holography has not been explored. So the outlook of the talk is the following. First of all is what is an S-fold, because most of you maybe never heard about an S-fold. So what is an S-fold configuration of type 2B? And the second is just how to place n equals 4, d equals 4 supergravity in type 2B. Actually, this was our paper. Our paper was to take this theory, place it in type 2B, compute the equations of motion of type 2B, and finding precisely the equations of motion that are in this box. Okay, it's like an alternative path to uplift n equals 4, d equals 4 supergravity, which has not been explored. Okay. Yeah, the uplift to 11D, so it goes through the 7-sphere, and then depending on the solution that you have, if you have a black hole, if you have a Janus, if you have whatever solution you have, then the 7-sphere will be distorted in one way or another, depending on what the scalars do, what the vectors do, but the topology is always the 7-sphere with different deformations. In type 2 is going to be something else, I will show you. So, good. So what is an S-fold? Let me start from a solution you all know. Take type 2B supergravity and place it on ADS5 cross S5. This is not an S-fold. This is ADS5 cross S5 solution of type 2B supergravity. So the geometry is like this. The ADS5 part, the 5-sphere part is a round 5-sphere. That's why there is an SO6 symmetry, which is the R-symmetry of superjam mills and so on. Then the radius of the ADS5, I call it G minus 1. So the radius of the ADS5 and the radius of the S5, they are related. They are the same. Then there is a 5-form flux, as you know. And then, and then there is the B2 and the C2 that I put together in this SL2 vector, which are 0 in the ADS5 cross S5 solution. And then there is the action and the dilaton, the Ramon-Ramon 0 form and the dilaton phi, that I will describe them by placing them into this 2x2 matrix that I call M. And then you know that for the ADS5 cross S5 solution, the action is 0, so this matrix is diagonal, and the value of the dilaton is a free parameter in the ADS5 cross S5 solution. So in the end, there are two free parameters, G and the value of the dilaton. And for the rest of the talk, I will fix them like this, just to remove them. But you can always reinsert different values if you want, okay? So I will fix, just for simplicity of notation, G equals 1 and phi 0 equals 0, okay? So this is ADS5 cross S5. But then this workshop is called, it has to do with low-dimensional holography. So you can ask yourself the question, can I replace for free ADS5, which is for dimensional field theory, can I replace it by ADS4, so I have low-dimensional holography? And then I will try to replace ADS5 by ADS4 cross a circle. So what happens if you do that? Does it work? And the answer is no, it does not work. What else you have to do? And then you have to do the following thing. So you replace ADS5, as I said, by ADS4 cross S1. This is good. You don't touch the F5. This is okay. Then this is again the B field. They are 0 as they were in the ADS5 cross S5. This is good. And the only thing you need to do is sort of like a minimal modification. You just have to take the action dilaton matrix. The action is 0, and the dilaton is just linear on eta. And if you evaluate the supersymmetry of the solution is non-supersymmetric. That's life. And the dilaton develops a linear profile. Then Monica said this morning, who cares about solutions with a linear profile for the dilaton? I will care about solutions with a linear profile of the dilaton. Okay, so essentially this talk is all about considering the linear dilaton profile seriously. Okay? So what happens, so I have this solution. Then, as Monica pointed out, how do you make sense of a linear dilaton profile, right? Because it sounds pathological, no? If it is linear and you make a circle, what is that? I mean, it's not single valued. Shall I throw away the solution? Let's keep the solution for the moment. So, yeah?
It's kind of similar, like, I mean, to DP brains, like, I mean, with E not equal to 3, right? I mean, like, there you also have this kind of...
So, yeah, I'm thinking of the D2 brain. Yeah, the D2 brain is non-conformal. So this case is, in that sense, yes. I mean, it's like a, In the deep brains, there is a moment in which the dilaton blows up really as a singularity, and this is more like a linear thing. I mean, it goes to infinity in one side, and yeah. So the thing is that, yeah, so we have a dilaton with a linear profile. And the next question is, can we make sense of this? Can we make sense of a dilaton with a linear profile? And then, in order to make sense of the solution, the only thing I will do is to rewrite this exact same solution in a more fancy way. What is the more fancy way? So what I'm going to show now is exactly the same slide as this, but just rewritten in a funky manner. So this same solution can be written like this. Okay? So what is this? So this is the following. So the entire dependence on the eta coordinate, which is the coordinate along the S1, so if you look at this, for example, you get e to the minus 2 eta for the dilaton. This is precisely what you get in here if this math frac M is just the identity matrix, and this A matrix here is this twist matrix over here. So what I observed by rewriting the solution like this is the following. The B fields, which were 0, they can be seen as the A twist acting on a vector of zeros. So this is sort of trivial, right? But then the axion dilaton matrix can be seen as the identity matrix being twisted by this A matrix. The geometry is the same, and F5 is the same. So what you learn from this is that a linear dilaton profile can be seen as a configuration in which all the dependence on the eta coordinate, which is the coordinate of the circle, is codified into this A matrix that is called a twist. Okay? It's just a way of really rewriting the same solution. But this is more illustrative. Why? Because what we learn from this is that what is happening is the following. Oh, there is something that is not displayed, eh? Ah, what a pity. So it's not, it's a pity, it's not, shit, it's not. Yeah, so I call this A because I decided that the way of twisting the B field is A, and the B field was defined with an index up, and therefore the M alpha beta matrix has the index down, and it must be twisted by the inverse of the matrix. It's just conventions. It's a pity because the next slide was really, it was a cool one. No, the other ones are fine, but the thing is that there was an equation here which was very important. Okay, well, let me try to explain the equation that is not there. So it's not my eye, no, it's not there. No one can see it, right? Okay, so let me explain with words what was in the equation. The whole point about this solution is that the entire dependence on the coordinate along the circle is codified in this A matrix, which is, by the way, an element of SL2, because you can see that the determinant is 1. So let's see how this matrix is appearing. And this matrix is precisely appearing in all the type 2B fields which are transforming under the SL2 symmetry of type 2B, which is called S-duality, right? So you see that the B field is twisted by the A matrix. In this case, it's trivial, but it's twisted by the A matrix. The axion dilaton, which is encoded in this M alpha beta, is twisted accordingly because these two fields transform under SL2. And then the geometry and the Ramon-Ramon form potential, which are SL2 singlets, they are not affected by the SL2 twist. So it's a way of knowing or somehow like clarifying the role of this SL2 matrix A and how this linear dilaton solution can be encoded as an A-twisted solution. So imagine I take this matrix A. I'm going to say that there is a circle spanned by this coordinate eta and of period t. So how do you evaluate whether a solution has a monodromy or not? You take this matrix A at eta equals 0, and then you evaluate the inverse of this matrix at eta equals t after going around, and then you multiply the two. So you multiply A of t times A inverse sorry, A of 0 times A inverse at t. And if there is no monodromy, then that thing is essentially is the identity, because you get A minus 1, you get the identity. It's a pity that this is the equation that is missing here, right? So if you compute A of 0 times A inverse at t, you get something different from 0. You get e to the minus t, e to the plus t, which is essentially telling you that the solution has a non-trivial SL2 monodromy. And this is why these solutions are called S-folds. And essentially what is going on is that in order to interpret the solution, you have one patch which is going once around the circle, but then once you go around the circle, you have to glue the solution with an SL2 transformation that induces an SL2 monodromy. And this is why it's called an S-fold. And this is allowed in string theory, because in string theory, you can glue different patches by using not only diffeomorphisms, but also using duality transformations. And this is an S-fold because of that, because once you go around the circle, you have to glue the solution in one patch to the solution in another patch by an SL2 transformation. That's why it's called an S-fold. There must be something localized there, but this is an interpretation of objects and so on, which goes beyond the supergravity approach I'm doing. Okay. Yeah, there must be some kind of object triggering the S-folding somehow. So, yeah, so then, as I said, the monodromy is e to the minus t, e to the plus t. And that is an element of SL2R. So you can tell me, no, but the string theory is nothing to do with SL2R. It has to do with SL2 set, because it's a discrete SL2. And then there is a way of making the SL2R monodromy, make it SL2 set. And the only thing you have to do is to go for a different solution that is created from the original one just by acting with this constant SL2. So the original monodromy, which was SL2R, now becomes precisely this monodromy here. So the monodromy now is SL2 set, and this is a proper background of type 2B string theory. Okay, so after people discovered these S-folds, in particular the S-fold that I just described, which is non-supersymmetric, then people were asking themselves, like, okay, is there a way of making a supersymmetric S-fold? And the answer was yes. And then people came out with this S-fold, which this time is n equals to 4. So it really preserves 16 supercharges out of the 32 supercharges of type 2B supergravity. So if you look at the solution, now the solution is a little bit more complicated because the geometry is more complicated. So the 5-sphere is spanned by these 3 terms here. So you have one coordinate, which is alpha, and then a 2-sphere here, a 2-sphere there. So the geometry breaks the isometries of the original S5, but that's life, it's not a problem. Then F5 is like this. And then, as I said, it is an S-fold because the B field is, again, the A twist of these B1 and B2, which are eta independent. And in the same manner, the action dilaton matrix is the A twist of this matrix, which is, again, eta independent. So it's just a more complicated solution, but the structure is the one of an S-fold. It's really all the dependence on the eta coordinate goes through the twist matrix. And this S-fold, this solution preserves, as I said, n equals 4 supersymmetry. So 16 supercharges. So then we just ended asking ourselves whether the conjecture by Gauntlet and Varela was correct or not, because some years ago, actually quite some years ago, they made the following conjecture. So any supergravity, in this case type 2B, any supergravity solution with a d-dimensional ADS factor, in this case the S-fold, which has an ADS4 factor, preserving n supersymmetries, in this case n equals 4, defines a consistent truncation of the corresponding supergravity, in this case type 2B, down to pure n equals 4, d equals 4 supergravity. So if this conjecture was correct, and indeed it is correct because it was proven by Davide and collaborators in this paper, a consistent truncation of type 2B supergravity on the S1 cross S5 must exist down to pure n equals 4, d equals 4 supergravity. So in the same way as there was a consistent truncation to 11D by Sveti, Liu, and Pope, there must exist a consistent truncation of type 2B supergravity on S1 cross S5, this is the answer to your question, so it was on S1 cross S5, there must exist a type 2B consistent truncation down to pure n equals 4, d equals 4 supergravity. So equivalently, the field content of n equals 4, d equals 4 must be embedded in type 2B in such a way that any solution of the 4-dimensional supergravity will have an uplift not only to 11D, but an alternative uplift to type 2B. Okay? So then we try to work out this uplift. At the beginning, we were wondering whether there was some kind of group theoretic procedure to work out the type 2B embedding, but there was no standard group theoretic procedure to do it, as people had done in the past for other truncations. But then the good news is that now, these days, there is this framework of generalized geometry and exceptional field theory, and by exploring it, you can work out the consistent truncation. So this is a highly technical thing, but the nice thing, the only thing I want you to know is that in order to work the consistent truncation out, there is a recipe you can follow, this is the recipe we figured out just by following or building upon previous results by Emmanuel and also by Davide and collaborators. And the point was the following. So if you don't understand this slide, it's fine. Like the point is the following. An n equals 4 solution of d equals 4 supergravity defines a generalized SU4 structure. Why? Because if the solution is n equals to 4, there will be an SU4 rotating the gravitini. So once you have a solution that preserves n equals to 4, that solution defines a very precise SU4, which is the SU4 preserved by it's the SU4 of supersymmetry. Once you have this SU4, the next thing you have to do is to localize, to embed that SU4 in the exceptional E7 symmetry of 4-dimensional maximal supergravity. Once you have this, you fluctuate exceptional field theory about this solution. And finally, the dynamics of the fluctuations will happen to be described by the pure n equals 4, d equals 4 supergravity. This is a highly technical thing, but it's just to show you that there is a prescription to work it out. And the final outcome is the following. So this is the embedding of the 4-dimensional fields in the 10-dimensional metric. This is the embedding of the 4-dimensional fields on the axion dilaton. This is the embedding of the 4-dimensional fields on B2 and C2. And this is the embedding of the 4-dimensional fields in the 5 form of type 2B supergravity. So essentially, from the geometry, you see the following. The 10-dimensional geometry, it has the 4-dimensional piece and the internal part. The internal part is given by this expression here. So you see that the 5 sphere is distorted. So you have the alpha coordinate, a 2 sphere here, a 2 sphere there, and in front of these two spheres, you get two functions, f1 and f2, which are precisely functions of the complex scalar in the theory, the complex scalar tau that I said before, that there is in n equals 4, d equals 4 supergravity. The same for the dilaton and for the action. So this is the 10-dimensional dilaton, this is the 10-dimensional action, and then you can see your 4-dimensional fields, chi and psi in the expressions, and also the function f0, which is given by this. So this is how to embed your 4-dimensional fields into the 10-dimensional scalars. Then the same for the V2. The whole thing is a bit more complicated. There is a component that is a scalar in 4 dimensions, and there are some components which are vector in 4 dimensions. And then you see that the scalar components depend on the scalars, and the vector components depend on the vectors of the 4-dimensional supergravity. So this is really like a plug-and-play thing. And then the F5 is a bit more complicated, so this is the 5-form field strength, and then you see that it depends on the field strength of the vector fields in 4 dimensions, F1, F2, and the self-dual F1 tilde and F2 tilde that I introduced at the very beginning of the talk. And then there are also these functions, B1 and B2, B tildes, which are written here. Okay? So the whole thing is that once you have a solution of pure n equals 4, d equals 4 supergravity, you can really plug it in here, and then you get a type 2B 10-dimensional solution. Okay? And nicely, the 10-dimensional self-duality of F5 boils down to the 4-dimensional self-duality between the vector fields. So it's something it's like a check that things are working properly. Okay? So how much time do I have? Because I'm essentially over. 20 minutes. Okay, this is going to be fun. This Docker et al. It is because in their case they work out, if I remember properly, the most general solution, the local form of the most general solution preserving 16 supercharges. So locally, this will fit into their classification, and the whole thing here is about the global thing, the gluing of the global form of the solution, which is the gluing with the S-fold and so on. Okay. So essentially, now whenever you have a solution in the n equals 4, d equals 4 supergravity, you can decide whether to place it in 11D or to place it in type 2E. So then, the outlook is the following. Take n equals 4, d equals 4, SO8 gauge supergravity with the field content I was saying before. So the first thing you can do is to place it in 11 dimensions through the ansatz by Svetik, Lu, and Pope. And the other thing you can do is to place it in type 2B on S5 cross S1 times the formula I showed you before. So now, what is going on now? If you just consider the ADS4 solution in this action, okay, in which the complex scalar is 0, and then you have an ADS4 solution, if you place it in 11 dimensions, you get an ADS4 which is dual to the 3-dimensional theory of ABJM. If you place it in type 2b, you get an ADS4 which is dual to the S-fold solution, which is called the S-fold CFT3 solution. If you compute now solutions which are ADS3, which are the Janus solution, if you place it in type 2 in 11 dimensions, you get what is called interfaces in ABJM. But then if you place it in type 2b, you would get what is called interfaces on these S-fold CFTs. And something I wanted to comment on this, because this is something we are working on at the moment. The Janus is precisely ADS3, and it only involves the scalars running. But something you can work out is what we will call the charge Janus, which is the Janus solution, but now you turn on charges for the vectors. This is a new type of solution you can construct, and what I can anticipate already is that once you turn on the charges, the effect is going to be the following. It's going to take the ADS3 of the Janus, and when you turn on the charges, the ADS3 is going to become a warp ADS3. So precisely when you write ADS3 as a Hopf vibration, ADS2 over a fiber, and you turn on the vector field along the fiber, precisely the effect of turning on this vector field is going to be deforming ADS3, keeping ADS2, and precisely ending up in the class of warp ADS3 solutions that we were hearing about this morning. So this might be a way of getting warp ADS3 in 11-dimensional supergravity or in type 2b supergravity, as you want. And it would be interesting to understand it in the context of either ABJM of the S-fold CFTs, and precisely to link to the talk by Monica this morning on this holography of the Kerr solution. So there is a way, it's just so there will be like this kind of warp ADS3 solutions we were listening about this morning. And then something else you can do is to compute black holes, asymptotically ADS black holes, in this supergravity here. Again, if you place it in 11D supergravity, then you will get the usual picture of ABGM placed on a Riemann surface, then you turn on some topological twist, and then you trigger a flow from ADS4 to ADS2, and you can do localization, microstate counting, and everything you want. You can take the Riemann surface to be a sphere, to be an hyperboloid, to be a spindle, which are solutions that are these days under investigation very actively. But then you can also place it if you want in type 2b, and in that case you will have an S-fold CFT3 placed on a Riemann surface with a topological twist, and then the Riemann surface could be whatever you want, and then you can ask yourself how the whole story about localization, etc., how it works in this type 2b. So just to conclude, maybe a bit too early, so maybe just to conclude, let me just show you the email we got from the referee report we got about the paper. And actually, if the person is in the room, so thanks, because we were very happy about the report. So the person said that this paper establishes very non-trivial new results. Actually, very non-trivial is very nice, because only non-trivial would have been enough, but very non-trivial is even better, right? So this paper establishes very non-trivial new results that could be important for the SCFT correspondence. And I just want to say that I agree with the referee report. So, thank you.